just going back to this one. Like this, these lines right here, I'm pretty sure this isn't quite the same thing, but it's related enough that I think it's interesting to talk about. Like if you go back to the economics, where like this is kind of like originating from, this line here, they can call it something called like the indifference curve. And the reason for that is I'm going to be happy at any point here. Okay? Now, there's going to be a level in which like, well, like, okay, all of these are like the best options, right? Right? So like this versus this versus this. Like how do I pick? Maybe I do have some underlying preference where at the end of the day I'm like, no, I really do want smaller price. Fine. But in general, you can get the sense that this is like I could be indifferent along here. Like I'm happy with any of these, actually. Okay? Does that make sense? Now, what's kind of neat about indifference curves, by the way, like this is on topic, off topic, is if you were to take two people, like let's say you had a limited set of resources, and yeah, let's say you had a limited set of resources, and that you have to divvy up between like two or more people, right? I could come up with like indifference curves. Okay? Of like where happy I'm going to be on these two things, right? Like let's say this is like the maximally happy I'm going to be, and this is how I feel, and this is how another person feels, right? Everybody's a little different. And what they'll do in order to like decide, it's kind of weird but interesting, what they'll do to kind of like decide like, well, how do you divvy up these things such that both people are happy? Like if I have a limited number of resources, right? Like if I give this person the point here, but then like I've used all of this person can't get as much of that, they'll have to go here, right? Like how do I decide where, like how to allocate it? And what they do, it's kind of funny. What they'll do is they just take this plot, put it on top of it, and rotate it. So you get something that like will look like this. This isn't the, oh, let's say I did this one. And so like if I rotate it, it'll look something like this. And then what you do is you find like this point. You're like, there, everyone's gonna be really happy right there, right? It's kind of a funny little thing. I saw you laughing. Did you learn this in economics? Yeah. There's a name for it, I can't remember. Pardon? It's like a box. Yeah, it's a funny thing, and I've never seen it before. Like I've only seen like this strategy of like flipping a plot in one place, and I just thought it was so peculiar, but interesting nonetheless. Anyways, maybe you've seen stuff like that in other cases, but whatever. And what course was that where you learned it? Another microeconomics?
Yeah, 301.
301? Who taught that one to you?
Jonathan Rosberg.
Yeah, everyone likes it. Everyone loves everyone in economics. Economics this is like a cliche among universities, is that econ departments are just so chill, and everyone loves them all. It's funny like that. Okay. Anyways, any other questions? And like, I mean, obviously we started PSO last time, but was there did anyone think of any questions related to like the multi-objective optimization? All right, cool. Okay. Okay, PSO. I'm recording, right? Yeah. Like I was saying last time, it was like, the story goes like it was inspired by observing like birds or schools of fish, right? And the whole point is, yes, every bird is like making its own decision, but they are influenced by the birds around it. In this particular case, it looks like they're trying to avoid, I think there's like a predator bird somewhere here. I think it pops up over here somewhere, right there. I think that's what this is, but they're like trying to get away, right? So each bird, like they kind of want to stick together, but they all want to move away from the bird, but they want to do it in a, you know, so, but at the end of the day, there's no real way, like they're not like, there's no like omnipotent decision making here. They're all acting independently while making observations sitting around it, and yet you get this like interesting like emergent behavior, okay? All right, PSO, is also like, okay, PSO, great, it's another like evolutionary computation. It's like primarily used for like real number, floating point number optimization. And it's really simple. I mean, don't get me wrong, GAs are simple as well. But yeah, genetic algorithms are quite simple. But PSO is very simple. And we'll see an example of that pretty soon. And they're also really easy to enhance, which is the general thing with like most forms of evolution computation by virtue of it really being just a framework that you then work within. Okay, particles. PSO, particle swarm optimization, is a population of, uses a population of particles, and each particle will represent some point in the search space. Now, this really is not unique from a GA, right? If you were thinking of like TSP, for example, the search space. What is the search space? Well, it is the set of all permutations, right? And you want to move, like each candidate solution would be a point in that set, right? Yeah? So same idea here. But like for our demonstration purposes, we're really going to be just like we'll take a function in some n-dimensional space, feed in the data points, and then get like a fitness value, or sorry, I'm getting ahead of myself, pardon me. All right, so, okay. Unlike chromosomes, these particles do not have traditional variation operators, so we're not going to be using mutation or crossover, even though we kind of are. Instead, the particles have a propensity to move towards areas of the search space that they like, while also being influenced by particles around them. We talked about this a little bit last time. Yeah, so in terms of optimization problems, each particle has a propensity to move towards the best area of the search space it is encountered, while also being aware of where the other particles are going to be going as well. Each particle has a velocity and an inertia, okay? Fancy way of saying, like, think of it like you're running, right? And if you decide you want to start going over there, you can't just stop immediately and immediately go that way. You kind of have to, like, okay, I got to, like, turn, right? You know what I mean. Okay, that's how the particles are going to operate. And you can like tweak these values, which we'll see shortly. So, okay, here is a two-dimensional problem, okay? But it's kind of trying to represent 3 dimensions of values here, but that's fine, right? We have a function of x1 and x2, or x and y, let's say, okay? A function of x and y. So, as a toy problem for PSO, we are going to say, given some function, it doesn't really matter what it is. I've got some function, okay? And I have it, I can ask, it's some written function, okay? I can ask it, okay, here's an x and a y, so let's say there's a point right here. And it's at like -2 and -1, okay? I can pump it in, and it gives me back a value. All right, that's the idea, okay? Now, this is a continuous space. So what this is trying to show is kind of like a topographical map of the fitness value is kind of like coming in and out. Well, it's also with the color, right? So more yellow, like over here, this is pretty high. Like think of this as like out of the page. And really dark blue is going to be like into the page. Do you see how it's kind of like trying to show depth here? Yeah? So this is how we're trying to visualize the 3 dimensions. It's a function of 2 dimensions that gives us a value, okay? So the point here is, where on here is the lowest point, okay? I mean, we can look at the particles. They're getting sucked towards here. Chances are, yeah, that's probably the lowest point. Looks like it even, right? Like that would be like into the screen. It's at like -5, you see? Where did this function come from? It doesn't matter. It's just some function, okay? Okay? We can think of it as like the fitness function. Now, it's like a ham-fisted fitness function in the sense that like, it's just some function. I know this is weird, but just bear with me, okay? It's because we always use these like arbitrary mathematical functions. Anyways, okay. The representation, it's going to be real floating point numbers. Thus, each particle will be an n-dimensional vector encoding its position, where n is the dimensionality of the problem. For example, in the above figure, like it's a two-dimensional problem. Like, so it could be a vector of 2 points. Okay? This is not to say that it only works on two-dimensional problems. You can have as many dimensions as you want. It doesn't really matter. Each particle has a position represented as an n-dimensional vector containing a position in space. Okay? That would be like this right here. Here's its position. Okay? So here is that particle's vector at some point in time. Okay? Just that's it. That's it. All right? A velocity, which is also represented as an n-dimensional vector containing deltas. Okay? A delta is like how much is it going to change over time. Okay? So that's also an n-dimensional vector. And like at time t, it'll tell us that particle's velocity. A particle's also going to have it's going to have access to its like memory of what's the best known location I've actually seen so far. Okay? So up here, it'll be like, let's say, okay, let's see here. It'll restart. Oh, that guy got sucked in. So they all kind of like went, okay, that particle went through, there was a particle, if you saw, it kind of went through and then it sucked back, right? It's because like, well, it knew that it had a best known location here and its velocity was so high, it went this way, but eventually it got sucked back towards where it wanted to go. You see? And in addition to that, it's going to have access to the swarm's best known position in space, another n-dimensional vector. Okay? Okay? So like these particles here are going to see like, oh, all the other particles are getting sucked over there. Maybe I should go over there. That's like the idea. Okay? Like, why would this particle decide to move this way, right? Well, because it knows that all these other particles are really happy over there. You might be wondering, though, like, well, why is it not going? Well, it's really happy with what it's got here, right? It's pretty happy. It knows all the other ones are over there, but it's pretty happy. And judging based on, like, what its velocity is, its inertia, the, like, weights of how much it wants to move towards its best known versus the population's best known. These are all values that we kind of tinker with, but we'll see in a moment. So any questions at this point? Usually the hardest part here, and maybe like PSO is always introduced with just some like arbitrary function. Okay, does this function have a name too? No, it doesn't. We're usually, when we're talking about TSP, we're talking about like, okay, the fitness function is the total distance of the Hamiltonian cycle, right? Here, the fitness function is whatever the output of this function gives me. Why? We're just seeing like how good can PSO be at finding the minimum value or maximum value of some arbitrary function. Okay? Velocity determines where the particle will be at the next iteration of the algorithm. Now, going back, right? The t here, time, really is like iteration number, okay? So time, it's like which step. And the t is only really going to matter in terms of t and then t plus 1, right? How to change between one time step to the next time step. One generation to the next generation. We don't call them generations, but they're generations. Okay, so the velocity, determines where the particle will be at the next iteration of the algorithm. In other words, the velocity t is used to determine the position of the particle at time t plus 1. That's what I was just saying, okay? Velocity calculation are okay, when you start your algorithm, velocities are usually going to be randomly set, okay? In addition to their starting locations, right? Particles are going to be like randomly started within some bounds, right? Here you would look, you'd be like, okay, well, each particle started between like -3 and +3, right? They're not starting at like -1,000, okay? And their velocities are going to be randomly set, but they're going to be bounded, right? They're going to be like maybe a velocity of like 0.5 or something. You're not going to have a velocity of like 1,000,000 because it's one iteration, the particle's going to go whoop, way out of the screen. So you bound them however you want. Now, what should these bounds be is going to depend on your problem and like what is the search space, right? But in this context, that's how you would kind of decide. Yeah, okay, so what do I say? Oh yeah, as the algorithm executes, the velocity of the particle is changing, okay? And the velocity is influenced by its best known location and the swarm's best known location, all right? So the velocity is what's changing, and the velocity changing is what changes the position as well. But the velocity is going to be like updated. So inertia is each particle has some velocity, and when particles' velocities are being updated, the change is applied to an already moving particle, okay? That's what I was saying before, right? If I'm running as fast as I can, like this shouldn't be mind-blowing, right? But like if I'm out in the field outside and I'm running